Today we're going to review this formula from yesterday for continuously compounding something. It's called A equals PE to the RT, or A PERT. And if you remember, we looked yesterday at how E is a number. And that number is kind of like pi, it's irrational. And here's what it looks like in your calculator. It's programmed in. Let's do e to the first power is about 2.71828. It goes on. So let's write this down. 2.71828. Okay, so yesterday we looked at problems where something is being continuously compounded, and there's this formula that we used, A equals PE to the RT. Here's what everything stands for. P is your starting value. It's called P. We think of principal and money, so it's your starting value. A is your amount over time. Where T is time. And R is your growth rate. In the A PERT problems, you don't need to add 1 to your rate if it's growing. You just put in the rate. So it says the formula A equals PE to the RT is often an accurate model for growth or decay problems because things usually grow or decay continuously, not at specific time intervals. For example, a bacteria population may double every 4 hours, but is increasing throughout those 4 hours, not suddenly doubling in value when exactly 4 hours have passed. So today we're going to look at how you solve an equation with this E, 2 ways, graphing and using logarithms. So the first question. A population started with 20,000 members and it grew continuously at a rate of 10% per year. How long would it take for the population to double? So let's open a new graph page and graph this. Alright, so let's open a new graph. Alright, so we start with 20,000 in our population. It's continuously growing, so E to the RT, and the rate is at 10% per year. So we change 10% to a decimal, 0.1. And then X is time. So we hit enter, nothing shows up because our graph should start at 20,000, not 6.67. So if we go to menu, zoom fit, it should pull that in for us. So you can see here's that 20,000, it's growing exponentially. There's our function. All right, this says how long would it take for the population to double? So we want to know when the amount, or the y value, equals 40,000. So let's type in that function. If I hit tab, we want to know when y equals 40,000. Alright, and we're looking for that point of intersection. Oops. So if I go to menu, analyze graph, find the point of intersection. Lower bound is to the left, upper bound to the right. There's our point of intersection. X is the independent variable, it's time. So this is saying at 6.93 years, the population is 40,000. Alright, so using this, our answer was 40,000. Or sorry, time 6.93 years. What's another way we can solve this? Well, let's look at the equation. We have 40,000. We want to know the starting value, 20,000, and we have growing continuously, e to the 0.1t. Alright, so there's our equation. Let's solve it. Let's get the base and the exponent by itself. Let's divide each side by 20,000. We get 2 equals e to the 0.1t. This is exponential. If you look at the exponent, it's a variable. So let's use a logarithm to solve. We have log, the base is e, make your loop, of 2 equals 0.1t. Whenever you see log base e, this is actually programmed into our calculator as ln for natural log, because it happens often in nature. So we're going to change that to ln of 2 equals 0.1t. To get t by itself, we're going to divide by 0.1. So we should get t equals 6.93 years. Let's try typing that in. So if we go to ln, which is control e to the x, there's ln of 2, and then go to the outside of the parentheses, divided by 0.1, we should get 6.93, and we do. So there's another way to solve, using something called the natural logarithm. 6.93 years. Okay. So the notes, when solving exponential equations that have a base e, we use a special logarithm with a base e called the natural log. So whenever you see log base e, change that to ln. Let's do an example. E to the x equals 16. Solve for x. It's an exponential. Let's use a log. Log base e, make your loop, of 16 equals x. Whenever you see log base e, change that to ln. ln of 16 equals x. X is by itself, so you type it in. Alright, so ln of 16, 2.77. So x is about 2.77. Let's try another one. Okay, we have solve for x as an exponent. Let's get rid of the 4 first by dividing by 4. We have e to the 2x equals, I believe this is 5.5. Let's use a log to solve. So we have log base e of 5.5 equals 2 to the x. Whenever you see log base e, change it to ln. To get rid of the 2, we divide each side by 2, and then we can type this in our calculator. So ln of, is it 5.5? Divided by 2, and we get 0.85. So x is about 0.85. All right, let's do one word problem, and then your assignment will be to finish 1 through 11, whatever we didn't do. So number 5, an organism can grow from 500 to 4,000 bacteria in 90 minutes. Find R for this bacteria if T is in hours. Okay, we're going to use apert. It's continuously growing. We want to know what equals 4,000. All right, we don't know R, but we know time. It's given 90 minutes, but T is in hours, so we have to figure out how many hours is 90 minutes. We can do 90 divided by 60. We get 1.5 hours, so 90 minutes is 1.5 hours. So we'll put that in for time. So again, we're plugging into this equation. A equals P e to the RT. Let's solve. Divide each side by 500. Alright, we get, oops, I did that wrong. Too many zeros. There. Alright, we get 8. 8 equals 1.5 e to the 1.5r. Again, we have this exponent we want to solve for. Let's use a log. Log base e, make your loop, of 8 equals 1.5r. Whenever you see log base e, change that to ln. Divide each side by 1.5. And then you can type it in your calculator. So in our calculator, oops, we have ln of 8 divided by 1.5, and we get about 1.38. So this is our rate. 138% is what it's telling us. Actually, if you're wrong, it's 1.39. Okay, so it's growing at 139%. Let's look at B. How many bacteria will there be in 6 hours? It's going to be a big number because in just 90 minutes it went from 500 to 4,000. All right, so we have A equals P e to the RT. The rate was that 1.39. And 6 hours, we're going to multiply this by 6. Let's type this in our calculator. Starting value was 500. E to the rate. Instead of typing the rate, I'm going to just use my last answer key so it types in that whole thing. And then this times 6. So here's our answer, 2.048E6, scientific notation. It means move the decimal place over 6 times. 1, 2, 3, 4, 5, 6. Fill those with zeros. So we're looking at 2,048,000 bacteria after 6 hours. So your assignment will be to finish 1 through 11, and we'll go over it tomorrow.